So yeah, welcome to session 20 of ITCS. So this is the second quantum session. And we have some talks on quantum complexity theory. And the first speaker is Abhinav Deshpande, who talked to us about the importance of the spectral gap in estimating ground state energies. So yeah, Abhinav, you can share your slides and you can start.
Can you see this?
No.
Okay.
Yeah.
Hi everyone, thanks for coming. So today I'll be speaking about this work, the importance of the spectral gap in estimating ground state energies. This is joint work with Alexey Gorshkov and Bill Fefferman. Alexey is at the University of Maryland and Bill is at the University of Chicago. And here's the archive reference. So let me start with the motivation and first by defining what I mean. So studying ground states is an important field in physics and maybe more generally across all of the sciences. So in this, we are interested in finding the ground state of an object called the Hamiltonian, which is simply, you can think of it as a function that maps a given state or configuration of a system to some cost function or an energy. And we want to minimize this cost function. And the ground state is simply the minimum energy configuration of some system. So no wonder it's useful in a lot of places like condensed matter, quantum chemistry, and optimization. So one question we can ask is how feasible is studying ground states of general Hamiltonians? And in the quantum setting, Hamiltonians are simply exponentially large Hermitian matrices. And the ground state is now just the minimum eigenvalue eigenstate. So in the quantum setting, there's this famous local Hamiltonian problem where, let's say we are given as input a description of some n-qubit Hamiltonian, H, which is a sum of terms Hi. And this Hamiltonian is local, meaning that each term Hi acts on at most, say, k qubits non-trivially. And as output, we want to estimate the minimum eigenvalue of H. So Kitaev showed way back in 2001, 2002, that it's QMA hard to solve this problem if you care about inverse polynomial additive error. And QMA is a quantum generalization of this class NP. So it's unlikely that quantum computers can solve this problem in general. More recently, this problem has been studied for inverse exponential additive error, and it was shown to be p-space hard. It was actually shown to be p-space complete. And this is what we call the precise regime, because we are interested in really precise estimates of the ground state energy. So in this work, we'll look at two ways of adding structure to the problem. So the first structural property we'll study is the spectral gap. The spectral gap is simply the difference between the two smallest eigenvalues of the Hamiltonian. And we want to study a variant of the problem where we are promised to have some spectral gap. Okay, so we want to decide between these two cases. In the yes case, the ground state energy is smaller than some threshold A. And in the no case, it's larger than some threshold B. And B and A are separated by some value delta, little delta, which is the promise gap. So the spectral gap is this difference between the smallest two eigenvalues. And in both the yes and the no case, we are assured that it's at least large delta. So these two are the important parameters in the problem. So again, little delta is the promise gap and capital delta is the spectral gap. The second structural property we'll be concerned with is whether you can have small circuit complexity of the ground state. So in this variant of the problem, we have the same parameters as before, plus we have the extra promise that there is some polynomial sized circuit to prepare a low energy state. And in this promise, we don't really care about whether finding such polynomial size circuits is easy or not. Again, so okay, we have the same parameters. And one interesting thing about this problem is that if you have such a polynomial size description of a circuit to prepare a low energy state, then the quantum then that can be sent as a classical witness to the quantum verifier. So for the experts, this is the analog of QMA, where the witness is classical, so that's QCMA. And in this work, we'll be concerned with this precise setting where the promise gaps are all exponentially small. And so when you don't have a spectral gap, meaning that you just have a vacuous promise that the spectral gap is at least 0, then these problems that I just mentioned about the local Hamiltonian are complete for these classes precise QMA and precise QCMA, which is just the analogs of QMA and QCMA with exponentially small difference between the completeness and soundness parameters. And it turns out that, these classes are quite powerful. Precise QMA equals P space, and precise QCMA is actually NP to the PP. Okay, so prior to this work, so this is what we knew so far. In the vacuous promise case, it's P space complete with a quantum witness, and NP to the PP complete with a classical witness. So our first result is that when you add a spectral gap of at least inverse polynomial, the complexity goes from P space to PP. So this extra promise sort of reduces the complexity. And now let's see what happens when we add this promise again of there being a classical witness. In that case, actually, the two classes coincide. So it's PP complete again in this case. So this means there's an equivalence between some variant of QMA and the same variant of QCMA. So that's it. So we've seen that the spectral gap can make the problem easier. And the fact that these two classes are the same might raise the question of whether the spectral gap promise is stronger than the low circuit complexity promise. So maybe if the spectral gap promise implies this other promise, then that would explain why these two classes coincide. And this is an interesting conjecture because if it's true, it would explain why, say, heuristic algorithms to find ground states seem to work well in practice today. And there are open questions about what the case is, what the constant spectral gap case looks like, and how this would look like in the non-precise regime where the promise gap is polynomially small, and so on. And I end with the limerick. Could I compute a ground state energy? Depends how precise you want me to be. It also depends on the gap. So here we give you a map of where it's P space and where PP. Okay, with that, I thank you.
Thank you, Abhinav. I asked all the authors to write a limerick for it. I was preparing for the discussion, but thanks, Abhinav, already for
all right.
saying it already.
Yeah.
And and the idea is that each one of the speakers will give their talk, and then we'll have all the questions at the end in a discussion phase.
Sure. Yeah.
Okay.
I'll stop.
So now we move to the second talk, and we have Chi-Ning Chou would tell us about the quantum meets the minimum circuit size problem.
Hi. Oh, yes, I can share screen now. Okay. Hi, everyone. Can you hear me clearly?
Yeah, I think it's pretty good. Yeah.
Right. And hello, everyone. I'm Chi-Ning from Harvard. And today I'm going to talk about this joint work with Nai-Hui, Jiayu, and Ruizhe on quantum meets the minimum circuit size problem. Yeah, and also I cannot keep track of time, so let me know if I only have 1 minute left. Yes. Okay, so maybe let me start with defining what's a minimum circuit size problem in the original classical setting to everyone. So in this computational problem, the input is a truth table of n-bit Boolean function and a size parameter s. Yeah, so this is like a truth table F. And the output is yes if there exists a circuit that computes this Boolean function of size at most s, and otherwise we'll output no. So notice that this computational problem is slightly different in the sense that the input length is 2 to the n. So when we say polynomial time, it is actually like a poly 2 to the n, so it's like a 2 to the n. And also a quick observation is that this MCSP problem actually is in NP, because there is a very simple witness you can have. It's just a circuit of size S, and we know that S will be at most 2 to the n. And the verification process can just like evaluate all the input and check whether it match the truth table. Yeah, so this is definitely an NP algorithm. Yeah, but it turns out that this is basically the best we know about the basic complexity result of this MCSP problem. And furthermore, like whether MCSP in P or MCSP being NP hard is a long-standing, very difficult problem. And there are actually also lots of barrier results showing that proving either requires some new techniques that's beyond the current complexity theory results. And furthermore, actually the best algorithmic result we know for solving MCSP actually is still brute force search. And some people even conjecture this is the case. Okay, so why MCSP? Like it seems that although it's a natural problem, and it seems that we still don't know it really well. But it turns out that in a setting of classical like a complexity theory, MCSP connects to lots of different sub-areas in TCS, including circuit complexity, learning theory, average case complexity, and cryptography. So this is like, I mean, the original motivation for us. Like, oh, what if we now study the MCSP problem in a quantum setting? Maybe it also have lots of connections to different subfields in like a TCS of quantum complexity. And perhaps like through the lens of MCSP in a quantum setting, this can give us some new insights. Yeah, so as a starter to like investigate the MCSP problem in the quantum setting, yeah, we now need to like transfer from like Boolean circuits to a quantum circuits. But immediately quantum circuits are different from Boolean circuits, because now a quantum circuit corresponding to a unitary transformation like this. In general, we have like lots of input qubits and some ancilla qubits, and the quantum circuits is like intrinsically compute some unitary transformation. So there are actually 3 natural types of computation you can think of the quantum circuit can implement. First, you can still implement a Boolean function in the sense that you look at the marginal probability of the, say, the first output qubit with a loss of generality and use it to determine whether the output is 0 or 1. And in the meantime, you can also look at the quantum state. This is related to the previous talk, where now maybe you fix the input qubit to some like O0 state with a loss of generality and look at the output state as your output. And also you can think of, oh, the whole unitary transformation is the function you want to compute. So this is already suggesting that if we want to study MCSP in a quantum setting, there are 3 natural like setting we can consider, and we actually consider all of them. But in order to properly define, actually it requires some extra efforts, but I won't describe here, but you're welcome to look at our paper. So this is a bird's eye view of the result we proved. So we have lots of results, but basically they can categorize into 3 categories. And the first one is marked blue. In blue, it is like some result that's already appeared in classical MCSP study. And basically by some direct techniques, we can prove it. And there is also some yellow result actually requires some extra techniques. Yeah, so that we can also prove it in the quantum setting. But the more interesting result probably is the red result, where we prove some quantum unique results. For example, we actually can show that for certain type of quantum MCSP, like for the state version and the unitary version, we actually can have some cool reductions that is not known in the classical settings. For example, some self-reduction or search to decision reduction, etc. And for the search, the state version of the MCSP, we also connected it to something like a pseudo-random state, etc. So it also suggests that, yeah, but as an initial study of MCSP in a quantum setting, it's connecting to lots of different areas, and also something that's only unique in a quantum setting. Yeah, and also like the study of MCSP in quantum setting actually is not immediate and trivial. It's still lots of barrier we need to conquer. And here I just listed 3 big categories. So it's like the quantum computation in general is erroneous and random, as opposed to the classical Boolean circuits. And also the introduction of the ancilla qubits turns out to be a little bit subtle. And also, it turns out that lots of our results actually specials to the gate set choice of the quantum circuits. And this is also something quite weird. And so just want to give people feeling like actually it's not an immediate extension from the classical setting. There's still some technical challenge. Okay, so in the rest of my talk, yeah, I hope I can use 1 to 2 minutes to convince you there are some interesting things in the quantum study of MCSP, especially I'm talking about this example of quantum unique reduction. But there are more, and you are welcome to look at the long talk or the paper. So let me use the state version of the MCSP to explain this quantum unique reduction. So in the state version, the input now becomes a quantum state, and maybe we have lots of copies, and the size parameter S. And the goal is exactly asking whether there's a circuit of size S that prepare this state. And now I'm going to show, so this is a decision problem, and the search problem is to find the circuits for me. And now I'm going to show you that, to convince you that actually there's a search to decision reduction. In particular, okay, we also have self-reduction and other gap version reduction. Yeah. And the key idea is the following: we can leveraging the reversibility of the quantum circuits to construct, to find us, to find the circuits using just the decision oracle. So now with the input is a quantum state, and we have a decision oracle. We can guess what's the last gate 1 by 1 and query this decision oracle. And if it output no, we can try the other one, and yes, and then we guess the other one. So we can keep doing this, and it is because the reversibility property of the quantum circuit, so that we can keep querying this decision oracle, etc. And of course, this is actually not exactly true. To make it work, actually requires some techniques. But the interesting open problem is then, oh, is there any application of this kind of quantum unique reductions? Okay, so as a quick summary, yeah, we studied like the MCSP problem in the quantum setting. In particular, our result basically can categorize into 3 steps. The first steps, we study the Boolean version. And then we also, in the second step, consider some quantum objects. And finally, we study some quantum unique phenomenon in the MCSP through the lens of MCSP. So let me conclude with some future direction. I'm not sure how much time I have left, but I just maybe stop here, and thanks for your attention, and you're welcome to ask me questions in the panel discussion or read our paper. Thanks, everyone.
Thanks a lot, Chi-Ning. So just to remind everyone, so yeah, we'll leave all the questions to the end for our panel discussion. So now we will move to the next talk, where Gregory Rosenthal will tell us about interactive proofs for synthesizing quantum states and unitaries.
Thanks. Hi, I'm Greg Rosenthal, and yeah, this is joint work with Henry Yuen on interactive proofs for synthesizing quantum states and unitaries. So first, let me talk about state and unitary synthesis more generally, and then explain what I mean by the interactive part. With state synthesis, the goal is to construct a quantum state, say given an encoding of that state in some succinct, reasonable way. And there are many examples of this in practice that one might care about. And similarly with unitary synthesis, that means the goal is to apply some given unitary transformation to a given input register. And again, there are many examples of this in practice. And relatively little is known about the quantum complexity of constructing states and implementing unitaries compared to what is known about the quantum complexity of decision problems. So why are these sort of problems difficult? Well, they can be seen as quantum analogs of function problems, where in a function problem, the goal is to map an input string to an output string. But there are at least three differences. One is that these quantum problems don't have any clear reductions to decision problems. Whereas with a function problem, computing each bit of the output string is just a decision problem if you compute each bit one by one, but that doesn't work here. Second, an n-qubit state has 2 to the n amplitudes, which in some sense makes it an exponentially more complex object than a string. And finally, in the case of the unitary synthesis, because we don't know what was in the input register, it's impossible to even give a classical description of the output register, regardless of any complexity constraints. So in this paper, we make progress toward what can be seen as an analog for quantum states and unitaries of the IP equals P space theorem. So what do I mean by this? We define quantum state analogs of a bunch of well-known complexity classes such as P space and QIP. We prove that state P space is contained in state QIP. And as a partial converse, we prove that state QIP is contained in state X. In the case of unitaries, we don't get as strong results. We only prove that a certain subclass of unitary P space is contained in unitary QIP. And also, we get similar results with multiple entangled provers rather than just a single prover. And these proofs reduce to QIP equals P space and MIP star equals RE, but these reductions are non-trivial. So first, let me describe the model of computation with state P, like QIP and state P space, for example. So the model is that there's a BQP verifier that will exchange messages with an untrusted quantum prover, and the prover can solve, as unbounded complexity. These are quantum messages over polynomially many rounds. Then the verifier will accept or reject, which so far is exactly like the model of computation in the complexity class QIP. And now what's different is that when the verifier accepts, it also outputs a quantum state. And these are the completeness and soundness conditions that we would like to hold. For completeness, there should exist an honest prover strategy such that with probability 1, the verifier will accept and output approximately the state that it's supposed to output. And for soundness, for all prover strategies such that the verifier accepts with non-negligible probability, the verifier's output state with this prover strategy conditioned on accepting should be approximately what it is supposed to be. Now, we define state QIP as the class of state sequences with one state on each number of qubits that can be synthesized as above. More generally, you could consider states indexed by binary strings. It doesn't really matter. We just need to consider some infinite state family, so we can use asymptotic notation. Unitary QIP defined similarly. State P space, and it's defined more precisely in the full version of the talk, as what I mean by approximately here, like just how small error we can tolerate. So now in the next couple slides, I'm going to talk a bit about the proof of state P space and state QIP. And because of time, I'm going to rush through it, but in the full version of the talk, I explain it more precisely. So first, the starting point is a protocol due to Aronson with a trusted prover for constructing a state, but where the prover is only allowed to send classical messages. So the solution is write the target state psi, decompose it in this way. First, the verifier will query the values of beta 0 and beta 1 to polynomially many bits of precision, construct this state beta 0, 0 plus beta 1, 1. Then it uncomputes the query, and then controlled on the bit I in this 1 qubit state that it constructed recursively construct theta I. And it's important to uncompute garbage because we don't want garbage to be entangled with the final state. So with an untrusted prover, we can do something similar because it turns out for states in state P space, these queries can be computed in P space. So the verifier can run IP equals P space in superposition. And this will defend against certain types of attacks, like cheating in the IP equals P space part of the protocol, but it won't defend against quantum attacks. And So in this thing here, I give an example. Say the prover a dishonest prover will in private construct some state phi sub x controlled onto query string x, and you can see how this fills down here. So our actual protocol, it's like the one on this slide, but it's a variant of it that defends against these sort of quantum attacks. Okay, now let's talk about this special case of unitary p space and unitary QIP. We say that a unitary has acting on n qubits has polynomial action if the subspace that it acts non-trivial on has dimension at most poly n. And this is done by a Hamiltonian simulation algorithm. We show that if we write u equals e to the it rho, then a certain purification of rho is in state p space, and the evolution time t is computable in p space. So then using state p space equals state QIP, the verifier can construct copies of rho and compute t and use this Hamiltonian simulation algorithm. Now with multiple entangled provers, we prove that state R equals state QMIP, where state R is like the quantum state analog of R. And this is very similar to the proof of state p space included in state QIP, or sorry, that's right. And the reason, I'll just briefly highlight why it's state R and not state RE. It's here when the verifier brute forces over all provers to find the honest prover. This it's guaranteed to terminate because we assume that an honest prover exists. And finally, a bunch of open problems. State QIP and state p space. Can we improve some of the approximation errors in our results? Can we reduce the number of rounds? We have a protocol with constantly many rounds that we conjectured works, but we haven't proved it. Is all of unitary p space and unitary QIP, as was suggested, polynomial action unitary p space. Can the protocol be generalized to mixed states? What if we require the provers to be efficient? What if the provers are unentangled? Interestingly, some of our proof steps break down if the provers are unentangled, even though it works if there are multiple entangled provers or just a single prover. And finally, is there an interesting zero knowledge notion of state and unitary synthesis or cryptography applications? Thank you.
Thank you, Gregory. And now, okay, we move to the next talk where Dorian Rudolph will deliver his talk on polynomially many queries to NP or QMA oracles.
Yeah, thank you. Can you see my screen? This is okay. Yeah, so my talk is on polynomially many queries to NP or QMA oracles, which is joint work with Sevag Gharibian at Paderborn University. First, I'll go over the motivation of this research and prior work. One may ask the question, what lies beyond NP? We have the polynomial hierarchy of complexity classes P, P to the NP, P to the NP to the NP, and so forth. On the second level of PH, there's delta to P or P to the NP. Generally, we say P to the C for the complexity class that can be solved. Generally, we say P to the C for the complexity class that can be solved by a polynomial time Turing machine with access to an oracle for a C-complete problem. To gain intuition, note that co-NP is contained in P to the NP. By restricting the queries the Turing machine is allowed to perform, one can define weaker complexity classes. In P to the NP log, the Turing machine may ask at most a logarithmic number of oracle queries. In P to the parallel NP, it must ask all its queries at the same time, so the queries cannot logically depend on each other. Generally, in P to the NP, the ith query depends on the answers to all previous queries. We can model these dependencies as a DAG, as shown on the right here. We interpret this graph as a circuit in which each node performs a single query with some preprocessing and then sends the query answer along the outgoing edges. By restricting the structure of the query graph, one can define complexity classes that lie between P to the parallel NP, which has been shown to be equal to P to the NP log and P to the NP. Recall that P to the parallel NP has non-adaptive queries, so they are not connected in the graph. Therefore, we add an output node representing the Turing machine computing the final output from the query answers. Gottlob considers the restriction of Kerry graphs to trees and shows that the resulting class called trees of NP is equal to P to the NP log. And our work is largely based upon this result. And yeah, we have the quantum analog of NP called QMA, quantum Merlin Arthur. And P to the QMA log has the physically well-motivated complete problem APX-sim, or approximate simulation, of simulating measurements on the ground state of a Hamiltonian. This raises the question whether the results for P to the NP log also translate over to the quantum setting. Here, P to the parallel QMA equals P to the QMA log has recently been shown. But it was not known until this work whether the result for query trees also holds. Next, I present the main results of our work. We consider a complexity class C of the given set. You can assume QMA or MA if you prefer for this talk. We define the class CDAG-S of query graphs with a bounded separator number S. Here, the separator number S of G is defined as the minimum S, such that every subgraph of G has a balanced separator of size at most S. Note that the separator number is bounded by tree width. Similarly, define CDAG-D as the class of query graphs of bounded depth D. And now the main theorem is that a query graph of separator number S can be solved by a Turing machine in time 2 to the S log n using S log NC queries. So for a constant separator number, we obtain that CDAG-S is equal to P to the C log for a constant S. This improves the previous classical as well as quantum results. For a polylogarithmic separator number, we get a quasi-polynomial time base with a polylogarithmic number of queries. Analogous results hold for query graphs of bounded depth. Next, we apply these results to APX-sim. Kitaev uses a circuit to Hamiltonian mapping in his quantum Cook-Levin theorem to embed a quantum circuit computation into a Hamiltonian. The lifting lemma then embeds non-adaptive QMA queries into APX-sim, preserving certain geometric properties of the underlying circuit to Hamiltonian mapping, such as locality, for example. The idea behind these geometric properties is to make the Hamiltonian more like a physical system. We extend this result to a generalized lifting lemma by providing a polynomial time many-one reduction directly from query graphs of bounded separator number or depth to APX-sim that again satisfies geometric properties. Now let's go over a few open problems. So we show that for polylogarithmic separator number, CDAG-S is contained in QP with polylogarithmic C queries. Is the quasi-polynomial time base really necessary here? Can we extend our results to further complexity classes, such as QMA1 with perfect acceptance probability, UQMA with a unique accepting proof, or stochastic MA, for which only some of our results hold? And what is the exact relationship between the separator number and tree width? Can tree width ever exceed separator number by more than a constant factor? So we know at most a logarithmic factor. And finally, I'll sketch the proof of our main result. The containment of QMA DAG of bounded separator number in P to the QMA log. For that, we need to evaluate a query graph of constant separator number with a logarithmic number of QMA queries. On the right side, you can see an example query graph. Each node contains a quantum circuit that receives outputs from incoming edges as well as a proof. The idea now is to define a total solution weight function T on the string of query answers X and proofs psi1 to psi(n). The functions Gi enforce a correct proof and a query string bit Xi. F of Vi is a weighting function that prioritizes correct answers to queries with more dependence. For example, Q1 in this example has a higher priority than Q3. We say a weighting function is admissible if f of v is at least 1 plus c times the weight on all outgoing neighbors for some constant c. If f is polynomially bounded, we can approximate the maximum value of t with a logarithmic number of QMA queries. However, f can in general be exponential, for example, for a line graph. Therefore, we need to transform the graph. This proof follows a similar structure to Gottlob's, but is adapted to probabilistic promise classes. Especially promise problems pose quite a challenge, which I elaborate on in the full talk. Before the graph transformation, we split the graph recursively using balanced separators to build a separator tree in which each node corresponds to a separator in the subgraph induced by its descendants. To transform the graph, we create copies of every node conditioned on nodes above and in the same separator. For example, we want to decouple the nodes V1 and V2, so these two nodes here. And now in the transformed graph, V2 chooses a copy of X2 conditionally. And so there's no longer this dependence here of V2 and V1. And hence, there are only edges to ancestors in the separator tree. And each node has therefore O of S times log n descendants, which polynomially bounds the weighting function. Lastly, here's the total solution weight function in more detail. G of I is defined such that if xi is equal to 1, then gi is the acceptance probability of the circuit qi. If xi is equal to 0, then gi is set to 1/2. Therefore, gi penalizes an incorrect xi. In the yes case, there is a proof that is accepted with probability at least 2/3. So by choosing xi correctly, we can increase gi by at least 1/6 compared to the incorrect xi. One can show two important lemmas. Firstly, it is possible to approximate the maximum t with QMA queries. Secondly, if t is close to the maximum, then x must be a correct query string. Therefore, we can determine the correct output xn using binary search. Thank you for listening.
Thanks, Dorian. And we're heading out to the last talk in the session. And Chi-Ning will tell us about circular bounds for lower energy states of quantum code Hamiltonians. The floor is yours, Chi-Ning.
All right. Everyone hear me? Okay. Hello. Thank you for coming. Yeah, I'm going to talk about a result of Anurag and mine on circuit lower bounds for low energy states code Hamiltonians. So to start off, the right question to think about is that ground states of local Hamiltonians, as we know, are highly entangled non-classical objects that happen to capture universal computation, quantum computation. But at the same time, we don't really understand anything past the ground state. Our understanding of low energy states which violate some fraction of the Hamiltonian terms or violate fractionally each Hamiltonian term, we are really kind of clueless as to the complexity of these states. So the goal of this paper is to somehow rigorously analyze and understand how entangled in non-classical states of low energy could be. And we'll do that in a very precise manner. So to preface, there was a conjecture formulated by Friedman and Hastings in 2014 called the NLTS conjecture, the no low energy trivial states conjecture, which posited that there were Hamiltonians, so physical systems one could write down on a piece of paper, local physical systems for which every state of low energy is highly entangled and non-classical, and they even provided a very rigorous definition of highly entangled and non-classical. And so these states are very nice because, as we've kind of discussed previously, these local Hamiltonians, they shouldn't have any classical approximation for the ground state. They can't be verified in, say, NP or whatnot. And they sort of form this very interesting separation that we always are looking for between quantum and classical. And you can sort of think of this as a state that if you started as a ground state and you connect it to a heat bath and let it thermalize a bit, then it would still be highly entangled. And so the goal of this work is to actually kind of work towards the NLTS conjecture, and it's to prove a circuit depth lower bound for every low energy state of local Hamiltonians. And we're not going to prove it for all local Hamiltonians, that would be impossible, but we're going to prove it for a specific family of local Hamiltonians, and those being local Hamiltonians corresponding to error-corrected codes. So this result is less of a construction and more of a necessary theorem that proves properties of all error-correcting codes. And how does this relate to NLTS? Well, the notion of highly entangled and non-classical that Friedman and Hastings conjectured was a notion of circuit depth lower bound. So they were trying to understand what is the minimum circuit depth required to build a state. And this is just a circuit where you just take, any two local unitaries and you just stack them one along another, and we're just concerned with the depth of this circuit. Previous talks in this session discussed this a little bit. So formally, what is our result? Our result said if you have a generic stabilizer error correcting code, an NKD code where n is physical qubits, k is logical, and d is the erasure distance, as long as the code is an LDPC, so it's got constant locality in both sides, if you write out the corresponding local Hamiltonian, which is just very simple, you just take a Hamiltonian term for every code check, and this is a linear transformation, but and you take any low energy state, whether that be a mixed state or a pure state, so any state rho whose energy is less than some number epsilon, then we should be able to prove a minimum circuit depth of generating rho. And what exactly do we prove? We prove the following result. The minimum depth is at least the min of log d, and log of something, I'm just going to say in a second, divided by n times a small factor of epsilon. And what's very interesting about our result is one would assume that the number that should go in this blue spot here is d, the distance of the code. Right? Distance would probably suggest what is the sort of gives the complexity. But what we actually show is that you can prove it with k. So as long as you can prove a circuit lower bound that's like minimum of log d and log k over n. So the relative rate itself seems to have a value in proving circuit lower bounds. And that's probably one of the more interesting parts of the result. And then we also show that you can actually strengthen this to make this log of k plus d. I'm hiding some stuff in the big O factor, but so you can show that either if a code is high rate or high distance, you can prove very non-trivial circuit lower bounds as to the depth of any low energy state. So example is that if you have a linear rate code and even polynomial distance, then anything of energy less than 0.99, n to the 0.99 is log n depth, which is optimal up to constants right there. So maybe some example codes as to where this takes effect. One idea is the Tillich-Seymour code, which is this hypergraph product code, which is a very simple construction, has been around for a long time, since 2009, where they quickly got a linear rate, but the distance was only square root n, but the lower bound we prove is just the same thing I just said of n to the 0.99 has log n depth. A more interesting construction that sort of defies our intuition as to what contains high complexity of entanglement and circuit depth, and maybe kind of provides insight into how we should think about this, is maybe the punctured toric code. That's where you take a toric code and you may start making these little holes, these green areas where you just remove the terms associated with them. And as long as you space these holes out by like n to the delta-ish distance between them, then you get a very high rate code and a very polynomial distance. And you just kind of apply the theorem, and presto, you get the result that's written right there, right? And it would behoove me not to say something about the recent results in quantum LDPC codes. And those codes are linear rate and linear distance codes. These are the ones by Pantelev and Kalichev. But interestingly, up to constants, our result is unable to prove anything better about them. So a very nice open question to consider is whether we can do better based on the construction there. But my suspicion is that would involve really opening up their construction, whereas the results that we state in this paper are very generic and are properties of all LDPC stabilizer codes. So maybe lastly, just why I think this result is surprising. I won't say anything about how the proof techniques. You can watch the full version if that's interesting to you. But the result, I think, is surprising because quantum error correcting codes were designed to correct discrete errors defined by the physical qubits, right? The notion of erasure distance is on physical qubits. And in contrast, we're showing the interesting property that low energy states, where even the low energy could be fractional violation, you could partially violate all the checks in some manner, the error correcting code somehow still is able to preserve this notion of high entanglement despite not being designed for this. It's sort of that somehow correcting discrete errors seems to have some properties of correcting continuous errors in some strange sense. And I don't really know how to say more than that, but it certainly, I think, is the most fascinating intuition that one should take from this. Lastly, if I have time, Alex, I could just say a little bit about the quantum PCB conjecture, but looking at who's in the crowd, I suspect that this is almost unnecessary. Right, so the quantum PCB conjecture, as you might know, is trying to understand, is it QMA hard to estimate the energy of a local Hamiltonian to a constant factor? And jury's still out on this, and we don't know if it's true. And the NLTS conjecture, the conjecture that we set forth trying to solve in this research, is a simplification which eschews the notion of computation from the problem and just asks, is there a family of local Hamiltonians where the circuit complexity is large? It sort of it separates the complexity of quantum states from the notion of computation which are both inherent in the quantum PCB conjecture. And we don't know how to solve even the simplified version yet. So our work, we hope, can be seen as some progress towards it, but I still think there's a lot to do, and I hope to keep thinking about this problem more. So yeah, that's the end of my talk. I guess, are we doing limericks, Alex?
So yeah, thanks, Chinmay. And so now after the talks, we will have a panel discussion. And as I asked the authors, they have written a limerick for their work. So I ask each one of them to read their limericks, and then we can start asking questions. So I think Chinmay, you can start like you have it already. Yeah. So go for it.
So this is my limerick I wrote yesterday. So for years, our community paused in perplexity, not understanding how to lower bound the complexity of any low energy state until we considered the rate of codes protecting in a quantum capacity. So
very good. Thanks
for the challenge of writing the limerick. It was fun.
And I think I'll ask now Abhinav to read his limerick again.
Sure, yeah. Okay, let me. Yeah, do you see this?
Yeah.
You see it now?
Yeah.
Okay, yeah. Could I compute a ground state energy? Depends how precise you want me to be. It also depends on the gap. So here we give you a map of where it's P space and where PP.
Thanks again, Abhinav.
Thank
you. Who can we ask? Dorian, can you do it now? Can you read yours?
Hey, okay. Each node in a graph asks an oracle, yet we seek to query logarithmical. So the weights ought to be light, the graph to be made tight, when its structure is aborical.
Chi-Ning?
Yeah, sorry guys, I actually didn't prepare it.
No, no worries. No worries.
Yeah, my English level is not as good, but I hope next year I can be able to do it. Yeah, but thanks for everyone's.
And so Gregory, yeah.
An analog for quantum states of QIP equals P space, and similarly for unitaries acting on a smallish subspace.
Thanks, Gregory, and thanks for everyone for keeping up the challenge. I think last year this idea is inspired by Aviad Rubinstein. He proposed something like this last year, and I found it fun. So I tried to put a bit more structure and ask the authors again. And thanks a lot. It was great.
Yeah, thank you, Alexey. I had fun doing this.
And now, okay, let's go after some art. Let's go back to science. So let me know. Yeah, do we have questions? So I think Sev had a question. So do you want to ask it out loud, or shall I do it?
It's up to you guys.
Go on.
Okay, so thanks to all the speakers, great talks. So Chi-Ning, I just had a quick question for you. So normally, of course, in quantum complexity, we tend to think of inputs to problems as being classical. And so, but it looked like at the end of your talk, for the one result you highlighted, the input was quantum. Is that correct, or how
yes.
are you representing it if not?
Yes. So actually, in our paper, actually we can define several different variants. Yeah, you can think of of course, the state being a quantum object, but you can also have a classical description. But that description might be a big circuit itself. So the question will then be like, oh, can you have a smaller circuits for the state computed by these circuits? Yes. Mm-hmm. Yes. Mm-hmm.
So yeah, I have a related question. So I think you have an open problem that trying to prove if either of these problems is in NP. But we have we have some QMA completeness of some problems that are related. For example, I think proving if a unitary is non-identity, or if a circuit is non-identity, or something like that. This is QMA complete. Have you thought if somehow putting this in NP would contradict, I don't know, would imply NP equals MA or something like that?
Yes, so actually, yeah, I mean, we do have some similar Berry result. Yeah, like showing like if you have an efficient algorithm, then you have lots of undesirable consequences. Yeah. But in the meantime, we also don't know how to show that it's like a QMA hard or something similar. Yeah, and in fact, the Boolean version, we show that it is in QCMA. Yes, so yeah, you probably also won't expect it to be QMA complete.
Okay, I see. Thanks. Anurag, you have a question?
Oh, hey, great talk, everyone. So question from Abhinav for his talk. In the proof of Pcb theorem, Denou's proof of Pcb theorem, there are these steps which amplify the gap of a Hamiltonian.
Yeah.
Which is unknown entirely in the quantum case. I wonder if the presence of a gap in the Hamiltonian could help prove such results, because classical Hamiltonians inherently have a spectral gap. So I don't know if that is a valid question here. But
so I believe, like to some extent, there are results which show that you cannot hope to have such, spectral gap amplification procedures. Wait, are you talking about the spectral gap or the promise gap? Which amplification?
Promise gap amplification for a spectrally gapped Hamiltonian.
Okay, promise gap amplification for a spectrally gapped Hamiltonian. Yeah, so then we have a separation, right, between precise QMA and, precise, the gapped version of the local Hamiltonian problem, which we prove is PP complete, right? So I guess if you believe QMA is not equal to PP, then we don't have such procedure.
But precise regime is probably something where the promise gap is exponentially small. Is that correct?
Oh, you're talking. Okay. Yeah, so about the non-precise regime, right. So it boils down to whether there's such a separation, right? My intuition, like, so if you believe the conjecture that I was making, is that the spectral gap would reduce the complexity even in the non-precise regime, so which would bring it down to QCMA, in fact, because the conjecture is like it's a stronger version of what we prove, in fact. Yeah, so I guess it all depends on your prior on whether QMA and QCMA differ.
Okay, thanks.
But yeah, actually, I had a question for Chinmay. So before your results, what were like the best known ones on what the lower bound is for the circuit complexity?
Yeah, that's a great question. For certain restricted classes of states, there were known results for log n lower bounds, so states which violated specific Hamiltonians. They were like the states called low error states. But I think as far as I know, before a result, there wasn't a well-known lower bound for all states of low energy, other than under energy, like order and the -2 or something. So in that you can kind of come from like circuit to Hamiltonian reductions. So proving lower bounds for all states, I think, is the principal difficulty.
I also have a question regarding your paper. So I didn't quite understand what is missing from your results that is not proving the conjecture.
Our circuit lower bound is a small dependence on the epsilon factor. So it's not proven for some fixed constant epsilon. So if you fix the constant of epsilon, you only get for a fixed constant epsilon, you get a fixed constant lower bound. You don't get a super constant lower bound, if that makes sense.
Oh yeah, okay. Thank you.
Questions? Actually, I have a okay. Go on. Okay, I have a question to Abhinav. So at the end, you said that somehow your results explain why we do have heuristics for these problems. But at the end of the day, like you prove PP hardness, right? So yeah, can you comment on that? Yeah.
Sure. Yeah. So I was talking about the stronger version of the result that we did not prove. So it will be the conjecture that I was making, which is saying that polynomial size circuits exist to prepare low energy states, and which is like a minimum requirement for these algorithms to work in the first place.
Okay. And another question. So the spectral gap, I imagine, is only important for proving soundness, right? For completeness, you don't really care about it. Or am I wrong?
Can you repeat? It's only important for what?
For proving soundness, somehow for the soundness part of the proof and not for completeness, or am I wrong?
Let's see. So like when we want to show the upper bound of PP, we do need the spectral gap there.
Okay. Oh, I see.
Because otherwise you can't do it precisely. Yeah.
Oh, I see. So okay. But then I imagine that for completeness, then do you need spectral gap on both sides for completeness and soundness on upper and upper, or like an upper bound maybe just in one and lower bound just in the other, or you need both spectral gaps on both sides?
I see. Like in both the yes and the no cases, you mean?
Yeah.
Yeah. So I think we can do away with the spectral gap in the no case. Because I think we use one of Self's results on how, or was it Andrus's results, where if you have a spectral gap, you can in fact compute spectral gaps in PP. So yeah, like we sort of check for spectral gaps, and if it exists, we just apply our PP algorithm, and if it doesn't exist, then we say no.
Okay, thanks. So I think Sev had a question.
Yeah, let me just also quickly comment on that. Like intuitively, I would expect that the spectral gap should come in the upper bound, right? Because usually having a spectral gap helps with state preparation, like
exactly
these things where you project onto the ground state or things like this. Like, so that's the feeling I have. Sorry, the question I had was going to be for Chinmay. So you mentioned these the recent coding breakthrough, right? You're not able to hijack that in your framework, right? So what exactly, do you have a sense of what breaks down? I'm just curious, like.
Oh, nothing breaks down per se.
Okay, yeah.
It's just that the lower bounds we get depend on log D, right? Like one assumption you make is you sort of take a correctable region. So the best bound you're going to get is log of the distance. So improving distance from root n to n doesn't really help with improving our result in that sense. Maybe something more specific about the way the construction is built, right? It's like this tessellation of these kind of squares.
Yeah, that's right.
Ways. Something would have to be used there to argue the bound. We have some ideas. I mean, I can discuss in greater detail at other points. There's sort of this, we have crude bounds as to how much like the errors propagate when when you're a low energy state, and one hope is if an explicit construction can help us sort of bound that better, then you might get an improvement. It might be enough. But...
Thanks.
Also, I have another question for Chinmay. Sorry. Is there some sort of wishful result which, if true and you plug in your results, would immediately yield NLTS, or is there not such a thing?
So the wishful result is not due to ourselves, but there was a result from 2015 by Lior Eldar and Aram Harrow, which says that if you are able to build a quantum locally testable code, so you have to add the local testability property to the linear distance code. And in that one, you didn't actually, the rate was independent. You were able to you were able to get the NLTS result. And the intuition there is that the local local testability sort of lets you switch from discrete errors to continuous errors. Like it provides you the tools to do that transformation. The surprising thing in our result is you don't actually need it to do it, but you can't do it as nicely as you want without it. And so look, yeah.
Okay, yeah, got it. Thanks.
So yeah, I have a question to Gregory. So like, yeah, you showed that state R is equal to state QMIP. So why can you expect that you don't need quantum communication, or is it somehow intrinsic?
Wait, you
okay,
mean as opposed to why not state RE equals state QMIP?
No, no, yeah. Why it's not state MIP star?
Oh, sorry. Oh yeah, state MIP star. Yeah, that's what I meant.
Oh, okay. Instead of Q,
so
so
I
you
think
don't.
it said state QMIP, which same thing. But
Okay, is it? So the question is like, do you know that in the state the state world they are also the same?
oh, I see your question. I don't know. Henry's in the audience. Yeah, Henry, if you know, you can chime in. Yeah, I think they should.
It's not clear to me.
Promote Henry to the panelists, otherwise he can't talk.
Okay, is Henry there? Okay.
He's in attendees.
Okay, a second. Maybe I can do that.
Yeah, I mean, I think they should be the same. Not 100%.
Okay, now Henry
sure.
can talk if you want.
Hello, can you hear me?
Yeah.
Oh yeah, that's a great question. So I guess the state MIP star would be a model where the verifier is quantum, the provers are quantum, but the communication is classical.
Yeah.
That's a good question. I don't know.
My hunch is, Henry, you can't do anything because at the end of the day, the blocks that the verifier has to build with are like polynomial circuits of Clifford gates and T gates, right? So like since he's bounded, we know the upper bound, there's only like 2 to the poly n states he could build anyways, right?
Yeah.
You can tell him whatever you want to build, but he just doesn't have the bricks to build the house, right?
Well, 2 to the poly n states, that encompasses basically all states if you would, because up to a reasonable approximation.
No, the number of states is doubly exponential in n.
Yeah.
N qubit states.
Oh, yeah, right, obviously. Oops.
Yeah, 2 to the poly n is like roughly the size of the basis, right? 2 to the n is the size of the
Yeah.
basis.
Yeah, my bad.
Yeah, it's a good question. I don't know, my hunch is similar to yours, Chinmay. I think somehow it shouldn't be possible to do, state synthesis for very complicated state, but yeah, I don't know if any proof or disproof.
And the point is that you need to query
light on QMA, QCMA, right? Because that's the whole point, is that can the verifier build the state even that is the solution? The idea is, like, I think we believe that some solutions just can't be built, right?
Yeah, at least in our approach, it's very important that the communication is quantum because the verifier is doing many queries in superposition.
I see.
Yeah, that's a good question.
And okay, in your long video, yeah, you talk about a constant round protocol. Like, do you have a candidate for that, or?
Yeah, we do.
Okay.
Yeah, it's like in the protocol we described, it's like a bunch of rounds, and like the state, grows 1 qubit at a time in each round. In the constant round protocol, like, the prover just sends sort of like a tableau of what the state after each round should be, and then the verifier just sort of picks a like random round and verifies that like the 2 states at the beginning ending of that round or like that transition is consistent. I don't know if that was clear. Probably not.
No, it is. It's just okay. Then you have to take care if they're entangled. It's just that I'm trying to think. Yeah.
Yeah,
Well,
yeah, it's something like that.
Is there? Yeah. Okay. So yeah, Yeah, I don't know if anyone has any other question, or yeah, I'd like just to ask Dorian a final question. Do you think that your characterization could help us to find new QMA or any new complete problem?
You mean a new complete
Or
problem?
no,
that's more
sorry,
physically
not QMA,
motivated?
not QMA. P to, like any complete problem for P to the this complexity classes. P to the QMA log, for example, instead of APX sim.
I mean, it is
on
a
top of
complete
that.
problem for P to the QMA log.
No, sure. Does your characterization allow us to prove new QMA, new P to the QMA log complete problems?
So I mean, there's one aspect. So I mean, we have this translation for the to construct APX sim variants with certain properties. So you can translate all these a query tree, a query graph with the bounded separator number into a APX sim instance with also certain geometric properties. I'm not sure if that answers the question.
Yeah, I was trying to think if there's some, I don't know, not an APX sim, but a new problem that it does not look like APX sim.
No, I think it mostly looks like APX sim.
Okay. Any other question? Yeah. If not, so thanks again for for the wonderful talks and the great discussion. So yeah, stay tuned for the next sessions.